Module 5, Session 3. Session 3 will cover the following content. Learning Outcome 2.4.7. Determine or prove maximum and minimum turning points. Learning Outcome 2.4.8. Determine the point of inflection of cubic graphs. And lastly, Learning Outcome 2.4.6. Draw graphs of cubic functions. Learning Outcome 2.4.7. Determine or prove maximum and minimum turning points. An important application of differentiation is plotting graphs of cubic functions. In Level 4, students need to know how to determine the characteristics of cubic functions and plot the graphs on the Cartesian plane. Students will need to be able to find the following in order to sketch cubic graphs: the y-intercept, the x-intercepts or the roots, the critical or stationary points, namely the maximum and minimum turning points, and the points of inflection. We will start off by looking at minimum and maximum turning points and points of inflection before moving on to actually sketching the graphs. Maximum and minimum turning points. Students worked with finding maxima and minima in Level 3, but now they will also work with the second derivative to prove the turning points are minimum or maximum values of the function. The gradient of the function at the turning point is 0, so we know that the first derivative will be 0 at this point. This gives us the coordinates for the turning point. The second derivative tells us whether the turning point is a minimum or a maximum point. If the value of the second derivative is negative for x, there is a maximum. If the value is positive for x, then there is a minimum. Here are the steps to follow when finding our turning points. Step 1. We are given the function equation. Find the derivative. Step 2. Let the derivative equal 0 and solve for x. This is the x value or x values of the turning point or points. Step 3. Substitute the x values back into the original equation to find the y values of the turning points. Step 4. Find the second derivative of the function. Step 5. For each x value, substitute into the second derivative and the following conclusions can be drawn. If the value of the second derivative is negative for x, there is a maximum. If the value is positive for x, then there is a minimum. Let's take a look at an example.
Calculate the maximum and minimum turning points of y is equal to a third x cubed plus 2x squared. What is very important here is, the key word is, we need to find the turning point first. And then we will prove which one of those coordinates, by using the second order derivatives, is your minimum and which one is your maximum. And when we consider turning points, what is the rule for turning points? Turning points, the first derivative is equal to 0. So that means it brings us to our first step. Y is equal to a third x cubed plus 2x squared. So we first need to find dy dx. And that is equal to a third times 3, that's 1, x to the power 2, plus 2 times 2, it's 4x, and then 2 minus 1, that gives you 1. After we got the first derivative, then we can write down the statement for turning point, because it's important. This is very important because we might do later point of inflection, and then their second derivative is equal to 0. For turning point, let dy dx equals to 0. It means that x squared plus 4x is equal to 0. Now we can find the x values. You can see as a common factor of x, we're taking it out. Then you see it's x plus 4 is equal to 0. Now we're going to apply the zero product rule. X is equal to 0 or x plus 4 is equal to 0. Therefore, x is equal to, you move the 4 over, minus 4. Now we have your x values of your turning point. So how will you find your y values? By substituting these values into the initial equation. Therefore, y when x is 0 will be equal to, so that's a nice way of writing it. Now that means we're going to substitute x with 0. That's a third 0 cube plus 2 0 squared, and you will agree with me, we got a value here of 0. And then what will y be when x is negative 4? Exactly the same, a third negative 4 cube plus 2 negative 4 squared, and if you use your calculator and you punch that in, then you will get a value of 10 2/3. You can test that on your calculator. Now you have your x and your y value, so now you can say therefore turning point coordinates are, the first one, x is 0 and y is 0, and the second one, x is minus 4 and y is 10 2/3. Right now we have answered the first part of this question. We have our turning point coordinates. Now one of these coordinates are minimum and the other one is maximum. So in other words, that's where the second part of our question will come now into play. We need to now, by using the second derivative, determine which one is minimum and which one is maximum. So in other words, we need to take note of the rules. When the second derivative is smaller than 0, then that's going to give us a maximum turning point. When the second derivative is greater than 0, that's going to give us a minimum turning point. So now we're going to do the proof. But I would like to first highlight the rules so that we can see what is the rules for minimum and maximum. Because you need to know the rules. I will just, in short, second derivative with respect to x, when that one is smaller than 0, that implies maximum turning point. Then that's rule number 1. Second one, second derivative greater than 0, that implies minimum turning point. Of course, you won't be able to answer this question without those rules. So let's start from our first derivative, right? dy dx, we've already calculated that. It was equal to x squared plus 4x. Is that correct? Therefore, our second derivative, d squared y to dx squared, that is equal to 2x plus 4. This is exactly the same as your second derivative with respect to x. Why I'm doing that? Because I'm going to use that notation. Now, we're going to use these critical points now. We're going to first substitute our x value with 0, and then we see in which category it falls in there. So in other words, my second derivative when x is 0, the critical points, that x value there, right, it's going to be 2, 0, plus 4, and you can clearly see the answer is 4. And 4 in this instance is greater than 0. In other words, when it's greater than 0, what does that mean? Therefore, now you look at the coordinate with 0, that one, your minimum, because it's greater. You can see the minimum turning point. The minimum turning point is, we use the small letter m for minimum, and it's going to be this coordinates, naught is to naught. Now, what will be your second derivative when x is negative 4? That's going to be equal to 2 negative 4 plus 4. Your answer here is because negative 8 plus 4, it's negative 4. And negative 4 is smaller than 0. Therefore, your maximum turning point. And from maximum turning point, we use the capital M. And it will be the other one. Negative 4 is to 10 and 2/3. And that is your final answer. That's why it's very important. You need to know those two rules in order to prove with the aid of the second derivative which one of these turning points are maximum and which one are minimum.
Learning outcome 2.4.8. Determine the point of inflection of cubic graphs. When working with cubic functions, in addition to maximum and minimum turning points, we can find another type of critical or stationary point, the point of inflection. This is a new section in level 4. Inflection means that the shape of a curve changes from convex or arched to concave or hollow. On a cubic graph, we find the point of inflection at the point at which the tangent to the curve changes direction. We find this point using the second derivative. The point of inflection occurs when the second derivative is equal to 0. Looking at this graph, we can see that at point A, the shape of the curve changes from arched to hollow. Therefore, point A is a point of inflection. Here are the steps for finding the point of inflection of a cubic graph. First, find the derivative of the function. Step 2. Find the second derivative. Step 3. Let the second derivative equal 0 and solve for x. This is to find the point at which the graph of the derivative has a gradient of 0. Step 4. Find the y value at this point by substituting the x value back into the original equation and solving. You now have the coordinates of the point of inflection. Look at this diagram of a cubic function. The derivative of a cubic function is a quadratic function, and it gives us useful information about the cubic graph. We can plot the derivative as a broken line on the same set of axes to see what the derivative tells us about the cubic function. The points where the derivative is equal to 0 give us the stationary points on the graph. In this case, they are also turning points. The point where the derivative changes from increasing to decreasing is the point where the cubic changes from being concave to convex. This is the point of inflection. It coincides with the turning point of the derivative. For some cubic functions, there are no turning points, but it is always possible to find a point of inflection at the x value where the derivative has a turning point. We use the second derivative to find the point of inflection because this is the point at which the gradient of the first derivative is 0. Let's look at an example of a lecturer finding a point of inflection.
Find the coordinates of the point of inflection of y is equal to x cubed minus 6x squared plus 9x. Point of inflection relates to the second derivative. In other words, my first phase of procedures here will be to find the second derivative. So I'm going to write down y is equal to x cubed minus 6x squared plus 9x. So my first derivative, dy dx, will be equal to 3x squared minus 12x plus 9. My second derivative, d squared y over dx squared. The derivative of that, 6x minus 12. After you found your second derivative, now you write down your statement for point of inflection. Because that's a condition for point of inflection. Let your second derivative be equal to 0. It means that 6x minus 12 is equal to 0. First remove the term, 6x is equal to 12. Then remove the coefficient, x is equal to 12. Divide by 6, therefore x is equal to 2. After we've calculated x equals to 2, now we move to our initial equation. Y, what will y be when x is equal to 2? We substitute 2 to the power 3 minus 6, 2 to the power 2 plus 9, 2. Use your calculator, you punch it in, and you will get a value of 2. Now we have solved your x and your y values, so now you write down your concluding statement. Coordinates. For point of inflection are, we use capital letter I, and then you put in my x value is 2 and my corresponding y value is 2, and that is your final answer.
Learning outcome 2.4.6. Draw graphs of cubic functions. Now that we have covered turning points and points of inflection, we are ready to plot the graphs of cubic functions. This is also a new section in Level 4. Let's take a look at the process. First, ensure that the equation is in standard form. The second step is to see what the general shape of the graph is by looking at the coefficient of the x cubed term. The third step is to determine the x-intercepts using the factor theorem and synthetic or long division. Fourth, find the y-intercept by substituting 0 for x into the equation and solving for y. The fifth step is to find the coordinates of the turning points if there are any. Last, plot the points and sketch the graph. Note that plotting the point of inflection as well can be a useful way to make your graph more exact. You will need to plot this point in cases where there's only one x-intercept and no turning points. Remember that we find the inflection point by setting the second derivative equal to 0. Please work in small groups to do this activity. Draw a sketch of the graph of f of x, clearly showing the coordinates of all the intercepts with the axes and the turning points. What mistakes do students make when they plot cubic functions? Discuss ways to support them. Please share with the group any additional tips or steps that you'd give your learners who struggle with these calculations. Let's watch a video of the solution.
Given the function of x is equal to x cubed minus 3x plus 2. And we have a question here, draw a sketch of the graph of the function of x, clearly showing the coordinates of the intercepts, meaning x and y intercepts, as well as the turning points. This is a cubic graph, so we need, what they mean here by this question is, we need to calculate first all the information that is needed for the graph. So, let's write down the equation first. Function of x is equal to x cubed minus 3x plus 2. Seeing that we need to draw the graph, the first thing that I would like to look at is the shape of this graph. So, what will be the shape of this graph? If you look at the coefficient of x cubed, then you will see that it's positive 1. It means that a is equal to 1. This is positive, so it means you're going to have that shape. Because the sign of a determines the shape of the graph. So first positive, then negative. That's the shape of the graph. Now you already know, as you're going to calculate the other information, your graph will look like this. Secondly, we're going to now find the x-intercepts. If y is equal to 0, find x-intercepts. It's always nicely to state what you are busy with. Find x-intercepts. If, obviously the function of x, because it's given as such, is equal to 0. What does that mean? X cubed minus 3x plus 2 is equal to 0. Take note, this is not a quadratic equation. It's a cubic function. And for cubic functions, in order to solve the x values, we're going to apply the factor/remainder theorem. In other words, we will start with an assumption, because first of all, we need to guess the first factor. So let's assume that x is equal to 1. So I will make if x. Let's test if it's one of the factors is equal to 1. Right? What will it now be? It implies that the function where x is 1, it's going to be 1 cubed minus 3 times 1 plus 2. And remember, if this is equal to 0, which is the case because 1 plus 2, it's 3 minus 3, that is 0. What does that mean? That implies that x minus 1 is, so it's a little bit of revision for factor and remainder theorem. Now we have our first x value. Once we got our first x value, then we can find the other values by either using long division or using synthetic division. So what I will do now is I will use, because it's important to state which method you're using, that you have two, synthetic division, so that I can also revise synthetic division. Right. X is equal to 1. That's most what we've sorted out. What's going to happen now? So what do you do first? You write down the coefficients for synthetic division. But what we need to take note of here is x must be in descending order. So in other words, you draw a line there and you write down the first coefficient, which is 1. Then you can see from there, and that's the tricky part here, there's no x squared, so you're going to write down 0. Very, very important. Then your x is -3, and then obviously your constant is 2, and then you draw the line there, and then you even draw a line here. And then you start right there by writing down a 0. Remember, this follows a nice pattern. Add, multiply, add, multiply, add, multiply, add. So 1 plus 0 is 1. Then 1 multiplied with 1 is equal to 1. 0 plus 1 is 1. Are we all together? 1 multiplied with 1 is 1. -3 and a +1 is -2. -2 multiplied with 1 is -2. 2 and -2 is equal to 0. In other words, that there illustrates to you that once you got a node there, there's no remainder. So obviously, what will your factors be here? Your factors then will be here. Obviously, it means that x cubed, because that's your initial one, minus 3x plus 2 is equal to, what's your factors? Your first factor is x minus 1. And now we're taking the other factors from here. X squared, because the first one is x squared, plus 1x minus 2. Let's move to the other side. Your next step now will be, we need to factorize that. There's your cubic function, there's your first factor, so we need to factorize that in order to find the other x values. So I will just write it down, x minus 1, and then x squared, because this must be equal to 0, plus x minus 2 must be equal to 0. Obviously, we can factorize. That is a quadratic trinomial, x minus 1. And then obviously, what will be the factors of x squared plus x minus 1? Very, very important here. What are the factors here? You can see there you're going to get a plus and a minus, xx. You need a plus 2, and you need a minus 1 in order to get a plus 1. So obviously you can see there x minus 1, 0 product rule, is equal to 0, or x plus 2 is equal to 0. Obviously x here is equal to 1. You're going to have two factors of 1, or you can see x is equal to -2. So in other words, therefore, your x coordinates are x is 1, y is 0, and x is -2, and y is 0. Now we're going to find Number 3. We're going to find your y-intercept if x is equal to 0. So you move to your initial expression, the function where x is equal to 0, which means all x's will now become 0. Minus 3, also 0, plus 2, and you can clearly see your answer there is 2. Therefore, your y coordinates, your y-intercept, coordinates are, remember here x is 0 and y is 2. The next that we will calculate now is our turning point coordinates. Turning point. So you people can see it's a lot of pre-knowledge because we've done this separately before. So now you're applying exactly the same thing. No, nothing different. Everything else is exactly the same. When you're talking about turning points, you're talking about first derivative. So I will write down the initial expression. X cubed minus 3x plus 2. Then obviously I will find my first derivative, f slash x, which equals to 3x squared minus 3. And then obviously this must be equal to 0. So 3x squared minus 3 is equal to 0. So I take out 3 as a common factor. So x squared minus 1 is equal to 0. Now I'm going to factorize and find my x value. X plus 1, a difference between two squares, and x minus 1. Therefore, x plus 1, 0 product rule, is equal to 0, or x minus 1 is equal to 0. It means that x is equal to negative 1, or x is equal to positive 1. Now, what will be my function when x is negative 1? My corresponding y value? Negative 1 cubed minus 3 negative 1 plus 2 plus 2. And you can see you will get a nice answer here of 4. What will be my y value when x is 1? Exactly the same. 1 cubed minus 3 times 1 and then plus 2. This one is, you can clearly see your answer there is 0. Therefore, turning point coordinates are, we can clearly see when x is negative 1, your corresponding y value is 4. And you can also clearly see when x is 1, your corresponding y value is 0. Now we have calculated everything. We've calculated firstly our x-intercepts, then we've calculated secondly our y-intercepts, then we have calculated thirdly our turning point coordinates, which means we have all the information now that is needed to sketch the graph. So now the next phase, we will now sketch the graph. So you always start when you sketch the graph by having your, obviously please you're going to use a ruler, y-axis. It's very important to label it. And when you sketch the graph, you're also going to have your x-axis. That's very important to label it. Then you have your origin. Now let's start with our x-intercepts. Our x-intercept was -2. I think you all agree. And our x-intercept, the other one was 1. We're just going to estimate now 1. Right. Our y-intercept was 2. We've calculated that. And then our turning points was -1, just more or less in the center, is to 4. So it's going to be there. And it's always important to indicate your turning point coordinates. -1 is to 4. And obviously this one here, which is 1 is to 0. Now, where do you start? You always start by sketching your turning points. There's a turn, you can see there, and then there's the other turn. And then you just join. You join through there, there, you go through there, join, and you go up there. And obviously, this is the function of x. And there's your graph. X-intercepts -2 and 1, turning point -1 is to 4 and 1 is to 0, and your y-intercept 2. And then you just sketch the graph, and it's very important that you also label the graph.
Let's explore the previous example a little bit further. What if we wanted to find the inflection point of the cubic function f of x equals x cubed minus 3x plus 2, and we found the derivative of f of x to be 3x squared minus 3. To find the inflection point, we need the second derivative of f of x, which is 6x. Then we set the second derivative equal to 0, so that 6x equals 0. We solve to find that x equals 0. Substituting back into our function to find our y coordinate, we find that y equals 2. So the point of inflection is at 0, 2. Which we can mark on our graph. We have finally come to the end of this section of work. We have seen that differentiation is a powerful tool in mathematics and that it is essential to get concepts right. We hope that this is a less daunting task for you after this math support package.